Hello and welcome. You will learn about the combinations of functions. In this lesson, you will learn how to find arithmetic combinations and compositions of functions. Relatively brief in comparison to some of my other videos, probably not as much material, we'll see. Let's begin with the arithmetic function operation. So I will begin by talking about using addition, subtraction, multiplication, and division with multiple functions. In this case, I'll only be using two of them. If you have two functions, f of x and g of x, and you wanted to add them together, you'll use this syntax or it will be provided for you. This means the same thing as adding f of x with g of x. So if you are given your two functions, you would write one here and write one there and add them together. And, which often happens, you can combine like terms, maybe even do some factoring along the way. But you get the gist of it. You add those two quantities together. All of these will appear in the same fashion. This one's going to be f of x minus g of x. Now, when you're subtracting, you really have to be careful about the fact that if you're subtracting a quantity, that you possibly put it in parentheses. I'll be sure to do an example with you and make sense of that one. Multiplication, you might see it like this with no operation in between, or you might see it with a little dot in between, like f times g of x. One or the other. They both mean f of x times g of x. In this case, I will be putting the dot. Otherwise, it looks too weird if it's not separated by one. Now, keep in mind, it's a closed dot. The main reason I won't be having this dot is to make sure to differentiate between this and what's called a composition of functions. Final one with division, we have f over g of x. It might be written more so like this. Just my software didn't really let me write it like this. F over g of x like that, which is, of course, f of x over g of x. Now, there's something very specific about division which you have to be careful about, and that is that you do not ever want to divide by 0. So there are major domain restrictions when it comes to this kind of guy right here. Your g of x cannot possibly equal 0 in any such scenario that you are doing something like this. Okay, so what I'll often do whenever I have these kinds of problems, I'll write this out first. It just looks cleaner to me. The perception is much more obvious with regard to what it is that I'm doing. So I'll be writing that out if this is provided. And but that's all they mean. So this is not f of g times x, but think of it kind of like a distribution thing. You are distributing the f with the x and the g with the x. But it's not f times x, of course. It's function of x. These are two different y values with regard to an x variable. Okay, let's start off with this example here. If f of x equals 2x plus 5 and g of x equals x squared minus 3x plus 2, we're going to find a couple things. Now, I have 8 different things to find here. F plus g of x and g plus f of x. And then we're going to do the same for multiplication, subtraction, and division. Now, you'll probably catch on really quickly with some that I'm actually going to skip doing, and you'll see the reason why. Because there's a main question down below. Are these combinations of functions commutative? Do they fall under the commutative property? Meaning, can we reverse the order and will they still maintain the value that they originally had? We'll see if there are special cases or if it's always true or never true. Okay, f plus g of x is f of x plus g of x. So what I'm going to do is I'm going to substitute 2x plus 5 in for f of x. And then x squared minus 3x plus 2 in for g of x right here. Now, the parentheses aren't necessarily needed in this case, but it's a good idea to practice, especially when you do multiplication or subtraction, I suppose. Because at this point, you know, you're not multiplying them with anything, so go ahead and just add on over. 2x and negative 3x combine to be negative 1x. The x squared hangs out right here, and 5 plus 2 is 7. So f plus g of x, sorry, I didn't really give myself room, is x squared minus x plus 7. It's a newly created function, in a way, based off that. You can graph it, which we'll actually do on the next slide. You can graph it, you can calculate it, you can actually find actual values based on what's there. Okay, so you have some options and some things to do here. Now, I'm only going to set up this g plus f of x to just show you that, first of all, it's g of x plus f of x. But my question to you as I substitute these values is this particular combination of functions commutative? Does it fall under the commutative property? As I write this out, is there any difference between this and this right here? And the answer is no. These values, these quantities did not change in any sort of way. The addition will not affect it in a way to make it happen. These guys are equal to each other. So under addition here, the commutative property does apply, as normally does. So there's no issue with that. Now, if there was a 2 multiplied in front of the G here, whereas there was a 2 multiplied in front of the F, okay, now you're looking at a different story, in which case there's nothing I can really help you with. That's not necessarily commutative property. But just keep that in mind. This is the same thing as that guy over there, so I should still be getting x squared minus x plus 7. So this is the same guy right there. So under addition, yes. Let's check subtraction next. Number 2, f minus g of x and g minus f of x. So f of x minus g of x will be this guy. And this guy over here is going to be g of x minus f of x. I'll just go ahead and get it started right now. Now we're going to see if that commutative property applies. And if it doesn't, I'll make sure to spell out the final answers for both of them here. So f of x is 2x plus 5. And again, the parentheses for this one might not matter too much, but for this one it really will. At least for the parentheses, I'm really showing what it is that I am substituting. That's always pretty important. So 2x plus 5 is just 2x plus 5. Now when I subtract, I'm not just subtracting x squared. No, I'm subtracting a negative 3x, which is positive 3x, and I'm subtracting a positive 2. So now I can combine like terms, and I'll get negative x squared. Looks like plus 5x plus 3. And that is for this guy right here. Okay, so obviously different from addition. This is a completely different looking function. They're both quadratic, but this one's a negative quadratic. Different y-intercept and such. This guy over here, let's see how it's doing. This is x squared minus 3x plus 2 minus 2x plus 5. Check out that quantity. We're going to get x squared minus 3x plus 2 minus 2x minus 5 for the same reasons I mentioned before. And now we will get x squared minus 5x minus 3. So as you can see, these are two different answers. Not much different, though. What's different for this one? Well, it's the I won't say the inverse, but every sign is different. Every sign is changed. Would that always happen? I suppose it would for subtraction, yeah. But no, under subtraction, it is not commutative. So again, commutative property just means if you have something like a plus b, then b plus a is also true. However, if you do a minus b, that's not necessarily the same thing as b minus a. That's only true if a and b are equal. Try 5 minus 3. Is that the same thing as 3 minus 5? No, one's 2 and one's negative 2. But they are at least opposite each other, just like this one was right here. So you can kind of see that idea and how that's working out and how I can use that to my advantage. Okay, I'm not sure actually what just happened. I had a little bit of a crash in my software, so I just reset it. So all my work wiped away for numbers 1 and 2, but obviously just rewind to that point to see those two. But those are gone as far as what I wrote. Now what I did have written here below was that yes, this was commutative under addition, but no under subtraction. The last thing I was stating was that under subtraction, at least one is the opposite of the other. Now, I don't anticipate another crash, but I apologize if something gets wiped away again there. Okay, so I only did, no, I take that back. I did both of these. So now I'm going to do multiplication number 3, f times g of x and g times f of x here. Let's see if these end up being commutative. So this is f of x times g of x. So this will be 2x plus 5 times x squared minus 3x plus 2. Now that's for this guy right here. Why don't I just go ahead and start writing this one out and either confirm or debunk the fact that, or the theory possibly that this is commutative. Are those the same? Come on, are those the same? These are the same, right? I don't want to do this one twice. for any sake, whether it's time or whatever else, but I don't want to have to do these twice. These are both the same thing if you multiplied them out. A times B and B times A are the same thing. So, I mean, in a nutshell, one thing I'm basically saying is commutative property applies as it's supposed to. It does under addition and multiplication. And just to save you kind of the suspense, it is not true under division. So I'm really only going to be doing one of the multiplication ones. I'll do both division ones, however, for you, because they are different. So for multiplication, we have a couple different ways we can go about this problem. I could just distribute 2x with all three of these guys right here, and 5 with all three of these guys right here, then combine like terms, which is exactly what it looks like I'm going to end up doing. Some people go for like a box method. You can put them all inside, or you can put them on the outside of these individual boxes and multiply them together. It's the same thing. It's just a visual aid for some. And sometimes it actually helps out more because you remember to carry over negatives in such a way. I'll show you what the box method looks like. I'm not going to actually do it. And assuming I added everything correctly, that's what I'd end up with right there. So once again, a newly created function based on what I had. If I did that box method I'm referring to, you might have heard of it as generic rectangles as well. You create a certain box because we're going to create a 3x2 grid here with terms that cannot combine, and inside becomes the product of whatever's there. So notice how that negative 3 multiplies with 2x, you get negative 6x squared. So you see how people do that, but then you have to write it out as a string and then combine like terms once again. So one or the other, you still get there. And remember, g times f of x is the exact same thing. Okay, number 4, f over g of x and g over f of x. F over g of x is f of x over g of x, which is 2x plus 5 over x squared minus 3x plus 2. And g over f of x is g of x over f of x, which is x squared minus 3x plus 2 over 2x plus 5. Now, if they were nice and kind, or if I was nice and kind rather, but when you have problems this way, you actually always hope for things to cancel out because they're more fun when they do. I did not create one that was cancelable, and don't try and create one where you're saying something like, oh, there's a 2 on top and bottom, yeah, those can cancel, yeah. No, it doesn't quite work that way. You have to have a common factor, a common multiple that exists on top and bottom that when you divide it, it becomes 1. This is not that exact case right here. Now, these are different, and there is something that I'm leaving out for both of these. Now, first of all, this cannot be further simplified. This can be written into factored form. I'll get to that point in a second, as could this. But we're done with what we can write, except for the domain, or domain restrictions in this case. Now, for this guy over here, I cannot let this become 0. Remember, g of x cannot be equal to 0. So this guy here could not be equal to 0. For the sake of time, I'll just tell you that this is a factorable quadratic here. This is x minus 2 times x minus 1, and that cannot be equal to 0. So if that's the case, both this and this could not, or neither this nor this could equal 0 at any one time. So I have to make sure I consider that x could not ever equal 2, and x could not, or x could not ever equal 1. I should really use the word or. Because if x is 2 or 1, you divide by 0, and that's a big issue. So we can't let that happen in this particular quotient. G of x divided by f of x, in this case, this denominator cannot equal 0, so I set up that condition there. And so 2x cannot equal negative 5, therefore x cannot equal negative 2 over 5. So you get both of those stipulations there. You get everything that you cannot be. And if they ask you to list the domain, it might not just have to do with dividing by 0. It might have to do with taking the square root of a negative number. Make sure you take care of any sort of thing that's being asked of you. Okay, if you were to graph a combination of functions, I'm going to give you a different set of functions here. They're still linear and a quadratic. But we can do this in one of two ways. You may always graph the result of the function combination, meaning if you figure out what that function combination was, like we do right here, you can go ahead and always graph this guy. This one in particular is harder to do. I'll go ahead and do this one with you. So I'm giving you f of x and g of x. I'm making a new function called h of x, which is the sum of f of x and g of x. So f of g of x is f of x plus g of x. And that's equal to negative 2x plus 5 plus x squared minus 4. Which when you write it in combination with everything, that is, sorry, this is h of x, by the way. So that is x squared minus 2x, I believe, plus 1. If you were to graph this, you can always use a table. You can use vertex as negative b over 2a. I'm going to go ahead and write this in vertex form, and that this is a perfect square trinomial right there. If this said y equals x minus 1 quantity squared, this would be plus 0 and times 1 right here. If you've seen this in some of my previous videos, what you're looking at right there is a quadratic. It's a parabola with a vertex at the point 1, 0, and a stretch factor of 1, and it's going upward. So this graph really just looks like this. Starting at 1, 0, I go up 1, over 2 up 4, over 3 up 9, etc. Save the talk about graphs for a different or a previous video, of course. And here is your h of x graph. This is the combination of both your, this is a combination of both of your other graphs that you had. Forgive me for not sketching a great parabola here. That right there is h of x. Now, what does it mean to be a combination of your previous things? Well, first of all, it depends on what your combination is. In this case, it's addition. When you are adding, what you are doing is you are finding out what h of whatever value of x is at certain x values. H of 1 must be 1 squared minus 2 times 1 plus 1. It's 1 minus 2 plus 1, that's 0. H of 1 is 0. H of 1 is 0 right there, 1, 0. That makes sense. Now, it's also the addition of whatever f of 1 is. If h of x is f plus g of x, then h of 1 must be f plus g of 1. So that's f of 1 plus g of 1. Now, I'll be getting into this on this side in a moment here. But f of 1 plus g of 1 is negative 2 plus 5. That's positive 3 plus 1 minus 4, negative 3. 3 plus negative 3 is 0. So when I combine whatever f of 1 and g of 1 are, remember, these are y values. When x is 1, we get the y values of 3 and negative 3. When I add them, I get 0. You can imagine if I did, you can imagine if I did f minus g of x, that I would get a completely different looking graph. Well, not completely different, actually. It would probably just be the upside down version of it. But I would be getting a different graph. And that's different because you'll be doing f of 1 minus g of 1 in that case. So it's different based on what it is that you're actually doing with your function. Just make sure that you're keeping in mind exactly what's going on. We are finding those values in that way. So let's say you're not provided an equation. Let's say you're only provided a graph. Now I'm going to draw the graphs of f of x and g of x for you based on the equations. But say you couldn't arrive at this. Say they only gave you the graphs of f of x and g of x. I'll make f of x in blue and g of x in red. And my previous talk, what I was just mentioning, has everything to do with this right here. So f of x is a linear equation, negative 2x plus 5. I'm just going to very briefly do that one using my line tool. And it's going to look a little something like 1, 2, 3, 4, 5 up there. It's going to look a little bit like that. Okay. 1, 2, 3, 4. 1 second. Right there. Okay. That's f of x. Now, f of x has some very distinct points that I want to point out, and I'll be doing these at the integers. So make this a little bit thinner and make my dots a little bit thicker here. I'll be looking at like 0, f of 0, f of 1, f of 2, f of 3. Looks like my line's not perfect anymore. There-ish. We're pretty good there. F of negative 1, f of negative 2. We'll fit as many as I could. Okay? This is for f of x. So let's say you're given that graph. And g of x, excuse me, g of x, let's say you're given this graph. Now this is x squared minus 4. So that starts at 0, negative 4 and goes up 1 over 1 as such. I'm making some pretty big points here. Okay, I'll fit these points. Whoops. And we will go ahead and draw that graph as a result. So you're given two graphs here. The best possible look of these two graphs as I can actually make. G of x and f of x. H of x is the combination of the two such that it's the addition of these two. So when I add f of x with g of x, I get h of x. So you're given these two graphs and you're trying to determine all the points in green for which I will plot h of x. What we did here, remember how we found h of 1. Okay, you can see it on the graph here, but h of 1 is also f of 1 plus g of 1. F of 1 means the value of y on f when x equals 1. What is the value of y when x equals 1 on f? When x is 1, y is 3. 3. 3. G of 1 is the value of y when x equals 1 on g. When x equals 1, what is y? Negative 3. Negative 3. So f of 1 is 3, g of 1 is negative 3, 3 plus negative 3 is 0. That'll be the combination for h, only because h is the sum of these two. Again, if it was a difference, it would be at a different point. So be keeping that in mind. Let's go back to f of 0, or excuse me, h of 0. H of 0 will be f of 0, which is at 5, plus g of 0, which is at negative 4. 5 plus negative 4 is 1. So the y value is, again, the sum of these two values, adding 5 with negative 4. Let's move back over to the right here at positive 2. H of 2 is f of 2, right here in blue, plus g of 2 in red. 1 plus 0 is 1. When x is 3, h of 3 is f of 3, f of 3, negative 1, plus g of 3, which is 5, negative 1 plus 5 is 4. I don't have any more points on the quadratic or anything else here, so let me go to the left now. At negative 1, well, I'm sure I could fit another point, but I'm not going to. At negative 1, f is 7. F of negative 1 is 7, and g of negative 1 is negative 3. 7 plus negative 3 is 4. And it looks like I can still fit one more here. We have f of negative 2, which is 9. G of negative 2, which is 0. 9 plus 0 is 9. And this point is symmetric across. Now I get this graph, and as you can see, it's the same as the other graph I just last had. So we can do it using a graph probably more so at specific values. Now you will take a look at the behavior of this guy at certain points, and you're going to see how it behaves more like a linear at certain points or a quadratic. This is a straight up quadratic in the end when you add the two. That quadratic really dominates the focus of this graph here. And that's h of x, using just the graphs based on the graphs I had to make, obviously. Okay, I'm going to lean now toward compositions of functions. Now, composition of functions is the process of combining multiple functions, where one function is performed first. So they're performed in sequence. One function's performed first, and whatever you get for that function, whatever the output is, becomes the input for the new function. It'll substitute. It'll take place of x in the other function. The composition of functions is written as such. It says f, kind of the letter O. It's like an open circle. F, O, and G. It's a small o, though. It looks like fog. It means f of g. So if I find f of g of x, we're finding f of g of x, like so. Now, here's where I was talking about multiplication. Make sure that it's not the same thing. You know, if I write that, that is not the same thing as f times g of x. This is why I tried to avoid doing the closed dot, to make sure to differentiate. This is not multiplication. No, you are taking a function of a function, or a function within a function. Do the inside function first and the outside second, meaning take g of x and then take whatever f of whatever that value is. And then we'll do that. Or likewise, we could do g of f of x. Now, I put inception here because I said a function within a function, like dream within a dream. Now, I made this cover myself, so I don't think any copyright claims are actually being kind of used or misused there. So let's do some examples here. Not too many. I just want you to see what this idea looks like, and then obviously we can go along with it. If f of x is x squared and g of x is x minus 3, we're going to find f of g of x first. Okay, it's probably good if you write some space in between that you really say, I'm taking f of this guy here. So if I'm taking f of g of x, I'm taking f of g of x, x minus 3. Okay, if I take f of x minus 3 will take place of x in f of x. Now, parentheses, of course, are very important. X minus 3 quantity squared, which becomes x squared minus 6x plus 9. So that's what that expands out to. Number 2, we're going to check and see are compositions of functions commutative. So basically, when I plug this thing in, do I get the left? If I did g of f of x, is that the same as f of g of x? Changing the order. Let's find out. Well, this is g of f of x. So this is g of x squared, meaning x squared is now going to take place of x in this equation right here. So that is x squared minus 3, which of course outside of parentheses is also just x squared minus 3. So f of g of x and g of f of x clearly did not give us the same thing. Even though both are quadratics, they are not both the same graph. They don't not both hit the same points at all real numbers for x within our domain. So are compositions of functions commutative? No. And that's a big fat no. It's possible that they can be by general happenstance, like you might just run into them being the exact same thing. There are times when they are always commutative, though. They are with what are called inverse functions. I'm dealing with that in my next video. So when you have inverse functions, yes, the f of g of x and the g of f of x are the same thing. Okay, number 3 I'm going to do in 2 different ways. I'm going to do it by evaluating f of g of 2 straight off the bat by substituting this in here. This will be 2 squared minus 6 times 2 plus 9, which is 4 minus 12 plus 9, which is negative 8 plus 9, which is 1. But I can also do it by taking the f of g of 2. Now, based on the way it's written, one way or the other might determine the way that you actually do this problem. If you found f of g of x first, you might be substituting 2 into this one right here. But if you didn't and it's written like this, it's likely that what you're going to do is you're going to be taking the g of 2, 2 minus 3, which is negative 1. You take that f of negative 1 and you substitute it into your f of x equation, negative 1 quantity squared, and that's 1. Which way was easier? It's debatable. This one actually didn't look too bad, depending on what the problems were. But if you had one that was really big, I would maybe do that one really big thing first, and then I would substitute it in straight up like this. So if you had a lot of different problems, f of g of 2 and 4 and 7 and negative 5, I would figure this one out probably first and then plug them in, instead of doing 2 different inputs and outputs and figuring all of that out. That takes some time. And g of f of 2, doing the same idea here, I could just do straight up 2 squared minus 3, which is 4 minus 3, which is 1. See, that one wasn't too bad. But now if I do the g of f of 2, I'll get g of 2 squared, which is g of 4, which is 4 minus 3, which is 1. So we're getting 1 for all of these things, whether it was g of f of x or f of g of x. Now, g of f of 2 and f of g of 2 were both 1. Is that coincidence? Actually, yeah, it was, because these are 2 different equations. If I did g of f of 3 and f of g of 3, I assumed to get different values. But what you can do that's not a coincidence is these are the same. Whether or not, and then these are the same. Whether or not you applied the 2 in this early onset scenario, or whether you applied it after you've taken the composition of functions, will still give you the same value as long as you do the math correctly. Okay, let's do a domain of a composition of functions, or domain of compositions of functions. There you go. When provided a composition of functions, consider their initial domain as well as any intermediate and final domain as to not ignore any previous restrictions on the independent variable. All right, so what does that have to do with here? Well, if you have f of x and g of x, and you're asked to find f of g of x right here, I'm going to go ahead and do that first. I have x squared minus 9 and the square root of 9 minus x squared. If I took the f of g of x, I'd be taking the f of square root of 9 minus x squared, which is the square root of 9 minus x squared quantity squared minus 9. Again, this is taking place of x over here. Square root of 9 minus x squared quantity squared is just 9 minus x squared. Minus 9, 9 minus 9 cancels out. You're left with negative x squared. So this thing down here, now this, if I see negative x squared here, I'm thinking my domain can be all real numbers because I can substitute any value in the world here and I will get a value out for this. So can we take f of g of 4? Well, f of g of 4 must be negative 4 squared. 4 squared is 16, so we'll take the opposite of 16, which is negative 16. However, when I said that you may do it here at the end or at the beginning, when you're substituting them in one point at a time, like g of 4 and then f of g of 4, we should be able to do both. So let me try and do that. Let me try and take f of g of 4 by taking g of 4 first. G of 4 will be square root of 9 minus 4 squared, which is square root of 9 minus 16, which is square root, f of square root of negative 7. Okay, we have an issue, taking the square root of negative 7. Now, it's extremely possible we can deal with imaginary numbers and such, but when it comes to a graph, because, look, I could keep going with this thing, f of, if you know anything about imaginaries, this would be I root 7, and I could substitute that in there, and, you know, I'm going to come up with the answer that I want. But the issue with this is, if I wanted to graph this guy right here, this is not a real number. This is an imaginary number. This is I squared times 7 minus 9. I squared is negative 1. So you still get it, but you got it through imaginary form. And if it asked you to graph this thing, okay, I wouldn't graph it with just negative x squared. I have to be very, very cautious of what my initial domain should have been. So when I'm keeping that in mind, and any intermediate final domains, you know, depends on how many functions, how many compositions you're doing, the initial domain here really mattered because the first thing I did was g of x. Now, g of x is right here. And g of x has domain restrictions because you might possibly take square roots of negative in this ordeal here. G of x, you cannot take the square root of a negative number inside here. So 9 minus x squared has to be greater than or equal to 0 in this case. If I add x squared, it would say x squared is less than or equal to 9. Take the square root of both sides. X has to be between the values negative 3 and positive 3, including negative 3 and positive 3. Now, this is the domain that must be applied the entire way through, even when I got to this negative x squared right here. When I found f of g of x is negative x squared only for this case. So the graph of this guy, just a very quick one, the graph of this guy would just look like this right here. It wouldn't go down forever. It only goes down when x is negative 3 and positive 3. And that's the final result. I can't keep going here because there are no values that exist in the real number plane. Those are not a part of it. So all I will get is just that graph right there. So I have to be very, very careful about what was happening there, that I did take the g of x first, and I have to remember its domain when considering doing stuff. Because if I'm going to take the g of 4, I should not be getting a good value out. This is a no-no. We should not be using this in this particular case, even though it did give me the same value out, because imaginary numbers still help us a little bit. Okay, now we're going to deal with compositions of functions in the real world. So I actually have 3 word problems for you. I believe this one is the least complex, at least in the sense of what you're given or what you have to do. And then we'll get to the most complex one by the end, obviously. Okay, so starting off here, the function f of x equals 0.06x represents the sales tax owed on a purchase with a price tag of $X. Now, before I actually even talk about the next function here, let's talk about this one. 0.06x means 0.06 times x. You're multiplying this number by x. This is also called taking 6% of x. And if x is a price tag for something, we're taking 6% of some price, of some cost. This is tax owed, sales tax, which is actually, I mean, I'm doing this in California, so if you're paying 6% sales tax, you're well off right now. We're at 9% or something more than that. 6% of the price right there. So the value that you get is not the entire price with tax. It is just the tax that is owed. Okay. So for example, if you had something that was $100, what you would get in this function, if you took f of 100, you'd be getting 6 as your answer. $6 is the sales tax you'd owe. Together, that is $106 owed. The function g of x equals 0.75x represents the sale price of an item with a price tag of $X during a 25% off sale. 25% off is the same as 75% of. How am I getting that value? You take 100% of what you have there, take 25% off of that, and you are left with 75. So 25% off means 75% of. I should put of. Off and of are 2 different words. They're not very different, just by a single letter. The same letter, mind you. And that's where we're getting our 75%, that's where we're getting our 0.75 here. This value was telling you you're taking 0.75 and multiplying it by x, so you're taking 75% of x, which of course is the same thing as 25% off x. So another way of putting this one right here to get to this 0.75x, you can take your whole price x and subtract how much 25% of x is, because that's taking 25% off. Combining like terms, 1 minus 0.25 is 0.75x once again. So that's how they're getting their values. The reason why I'm saying all of that is because this might show up later. Or also because, you know, they give you the functions this time. What if they didn't? Right? You want to make sure you know what you're doing with it. Write the function that represents the sales tax owed on an item with a price tag of $X during a 25% off sale. So what they're asking you to do is write a composition of functions. And nothing else with that. I'm not asking you to do it for a certain thing, but I think I will. And I think it's important to be calculating a little bit of this. Write the function that represents the sales tax owed on an item with a price tag of $X during a 25% off sale. So what's happening here is you are actually doing the 25% off sale first, right? What tax is owed on an item after you get 25% off? So if we are going to be doing this function here, we want to do this one first, and then the sales tax second. Now, the reason why I'm writing it in this order with left and right is because sales tax represents f of x, and I'm going to take f of g of x. If I do it writing it like this, I'm going to take g of x first, then I will take f of that value. And is there a difference between taking f of g of x and g of f of x? Sometimes there is. In this case, I'm not so sure that it actually is, but it's good to make sure that you note that difference, because when it does matter, it's going to be super important. So I'm going to take f of 0.75x. Now again, what that says is I'm going to take 25% off of an item, and then I'm going to establish what the sales tax is for 25% off of that item. So 0.75x will take place of x in this expression right here. Okay, so 0.06 times 0.75x, let me try and do that off the top of my head for a moment. I think it's 0.04, shoot, I don't want to do this wrong. I think it's 0.045x. I think that's right. The decimal, Let's go ahead and assume that that's right. Let's see if this, you know what, actually, yeah, that makes sense with what we're doing here, because this is 75% of 0.06. So keeping all that in mind, let's say that you had a price for something that was $100, okay? The sales tax owed for a normal $100 thing would be 6% of that, which would be $6. However, during this sale here, we're going to take 25% off of 100. So that would be $75. The sales tax of something that is $75, 6% off of that apparently is $4.50. Apparently, because when I take f of g of 100, I'm getting 0.045 times 100, which is 4.5. Now, your final answer here, this is not a percent. This is currency. Because your last amount that you're referring to, or any of these things you're referring to, is dollars, right? The 25%, those are rates that we're referring to right there. We do the rate with that dollar amount. This final amount is money. So $4.50 is owed on a price, on an item that was originally priced at $100. What happened in between? 25% off, and then the 6% of that. Suppose you are shopping in a store that is having a 20% clearance sale. 20% also, or clearance sale also means 20% off. If it was 20% of, that would be a great sale. 20% of what it previously was. No, 20% off. So what is that of? 100 minus 20? That's 80% of. You also have a coupon worth $5 off any item in that store. These discounts can be stacked, meaning both can be applied for any item. Okay, sounds good. So we can take that 20% off and then get $5 off of that, and or might be able to do $5 off and then 20% off of that. Write functions to model discounting an item by 20% and to model applying the coupon. So we have two different functions here. We're going to write for f of x, and we're going to do also for g of x. How about that? F of x, let's let f of x represent the 20% off clearance sale. $5 off will be g of x. So if x, now it doesn't say it here, I probably should have written it. If x represents the number of dollars for a single price item, just like we had for the last one there, then we could be able to find these ones out here. F of x would be taking 80% of x. If x is the number of dollars of the item, let's take 80% of it. That's 0.8 or 0.80, which is irrelevant to have that extra o, but some people are very comfortable with it. I actually almost am not. I'm going to take that out right now. 80% of x there is 0.8x. Okay. G of x is $5 less than whatever x is. You take your price, you subtract 5 from it. So we have two different functions here. F of x represent 80% of, or 20% off, and g of x, $5 off right there. These are two separate things. These were not stacked at this point. How much more is any item if the clerk applies the coupon first? And I think that they mean more than compared to applying the coupon second. So what we have to do in this problem here, without it actually telling you, is we have to find out what f of g of x is, and we also have to find what g of f of x is. Because what it's saying is, all right, let's say that you went up to the register and you ended up saying, I want to apply my $5 coupon. And the clerk ends up saying, okay, I'm going to take $5 off, scans your item, then takes 20% off, and then says your total is this much. As opposed to if you go up there and the clerk takes the 20% off, because that's obviously the clearance sale, and then you go, oh, and I have a coupon after they tell you the price. So we're trying to see if there's a difference between the two without even actually using an actual value for x, which of course I will for you. That's part of my nature. Now, the difference between these two is this one here, if you take f of g of x, of course you do g of x first. So that means that you take the $5 off first. And then you apply the coupon. Whereas this one, g of f of x, says that you take the 20% off first. And then the $5 off. So if the clerk applies the coupon first, now they say how much more. So it makes it seem like if you apply the coupon first, you might be spending more money. So we'll see about that. So here we go. F of g of x would be f of x minus 5. And that is 0.8 times x minus 5. If I distribute that, that'll be 0.8x minus, I think that's 4. So that's a pretty good number. Pretty clean. This one over here, if I do g of f of x, I'm going to take g of 0.8x. That is f of x, so that will be 0.8x minus 5. That's it, nothing to clean up. So you can see the difference between these two. If you have some price at x here, you're going to take, essentially, if you do both of them, depending on the order, in this one, it's the equivalent of taking 80% of that price and then taking an extra $4 away. This one's equivalent to taking 80% of the price and then taking $5 away, which this is literal because you take the 20% off first and then you take the $5 away. The reason why this one's different is because if you take that $5 off first, it's like you're also taking the 80% of the $5 that you took away. So that's no good. So if you compare these two, you are spending, if X is all about money, you are spending how much more? You spend $1 more, because -4 versus -5, taking away 4 versus 5, if applying coupon first. Don't believe me? Let's try a real number. Let's try a clean one that'll work out. What can I multiply that by? How about 50? Let's do f of g of 50. A shirt is $50. Pretty expensive shirt, I guess. But a shirt is $50 here. We want to find out if we take off $5 first here and then apply the coupon, it would come out to this. 0.8 times 50 is 40. Minus 4 is 36. $36 for the shirt after both items are applied. For this one, if we do g of f of x, of 50, excuse me, that's going to be 0.8 times 50 minus 5, which is 40 minus 5, which is $35. And that'll always be the case. And you might be wondering, wait, how come we're doing it in this function? Well, we calculated it so it had this function. Because you might be saying, I don't see you taking the $5 off. Well, again, if we did it in order, we would do 50 minus 5, which is 45. That's $5 off. Apparently, 80% of 45 is 36. And I think that's correct. 36 over 45 is 4 over 5. So, or 8 over 10. So, yes, compared to it, it's that. So you'd be spending $1 more, which you're like, oh, that's not much. You're right, probably isn't that much. Depends on the item. The item was $100. The two differences in dollars isn't going to be that much. Whereas if it's $10, a dollar still feels like a heck of a lot more. So that's resolving that problem and using an example with it. But these were the key parts right here, the compositions of functions, where you could answer the question. Okay, one last problem, and there are 3 parts to this problem. It doesn't mean they're all separate things. You just, they might be. The number of bacteria in a refrigerated food is n of big T, because there's a little t later. It's 20t squared minus 80t plus 500, where t is between 2 and 14. What does all this mean? They tell you. Well, n is number of bacteria. This one is not spoken of. N, well, sort of. Then a number of bacteria. Let's just put n. So T, big T, is the temperature of the food in degrees Celsius. So you have refrigerated food. Now this has a domain restriction here. Apparently your refrigerator can only go between that and that, or something like that, right? Your temperature in degrees Celsius can go between 2 degrees Celsius and 14 degrees Celsius. That's when it's refrigerated. So you can set the fridge at those points, and or when you place it in the fridge, it might be as much as 14 degrees Celsius. And I don't remember my conversions of Celsius and Fahrenheit. I mean, I know them. I'm not going to do them. But that's pretty warm for refrigerated food, I guess. That's kind of disgusting also when you think about it. Certain temperature for food will give you more bacteria. I mean, that seems like a lot of bacteria. I don't really know how much bacteria should be in food. I really hope none, but apparently that's not the case. When the food is removed from refrigeration, the temperature is this. So you have your temperature as a function of time, where it looks like if the time increases, the temperature of the food increases, and it's linear. So it looks like if you take it right out at time 0, the smallest temperature you can get is 2. And that makes sense because that's what the refrigerator can set it at for the coldest. And we are only going to set our time between 0 to 3 hours. I assume if you go more than that, it either upsets something within here, within what we are trying to look for, or you best not eat the food because 3 hours for something that's unrefrigerated is quite some time that's supposed to be refrigerated. Let's find the following. The composite n of big T of little t, what does this function represent? So if we take n of t, we are taking n of 4t plus 2. And n of 4t plus 2 is 20 times 4t plus 2 quantity squared minus 80 times 4t plus 2. I'm going to be doing this without a calculator. We'll see how I do. Plus 500. So that is 20 times, I need a lot of room for this one, 16t squared plus 16t actually, plus 4, minus 320t minus 160, distributing the negative 80, plus 500. 20 times 16 is 320 t squared plus 320t, plus 320t plus 80, distributing the 20, minus 320t minus 160 plus 500. I should have combined those. Oh well, let's do it now. 320t and negative 320t cancel out. 80 minus 160 is negative 80. Negative 80 plus 500 is positive 420. So assuming I did all the work right here, we are looking at this. And I'm going to leave it like that. It looks like I could factor 20 out, but I'm just going to leave it like that right there. So this is n of t of t. Okay, what does this function represent? Okay, I want to show you in a couple different ways and see if it'll actually make sense with what it is that we're talking about. Little t is the time, it's the amount of hours that something is spent out of the fridge, that your food is spent out of the fridge. If we do 0 hours out of the fridge, okay, 0 hours out of the fridge, there will be 420 bacteria in our food, which I guess, it seems weird. I don't want to eat dinner tonight now. But 420 bacteria of food, if we take it out of the fridge at its coldest possible temperature we can do. Now, why does it become that? How come it's not 500? Well, because your temperature can't be 0 degrees, right? When your time out of the fridge is 0, when you take it right out of the fridge, you're at 2 degrees. And at 2 degrees, apparently, if I substitute 2 into here, I'm guessing I'm going to get 420. I'm not going to try it, but that's what it's saying. And every single hour that it's out of the fridge, well, every single second that it's out of the fridge, it's exhibiting some sort of quadratic behavior here. And I actually don't know what this one literally would look like other than, because I'm not going to graph it, but just kind of right here, we're looking at a domain between 0 and 3. 1, 2, 3. And here's 420, okay? We're ignoring this right here because this is when it's in the fridge. When it comes out of the fridge, though, it's shooting up like that and shooting up pretty high. 320 t squared, that's a large stretch factor. So your bacteria increases not only a lot, but in quadratic behavior. So it's going to increase more. Again, I don't know anything about bacteria. Ask a biology teacher. I assume that the bacteria is reproducing or something at that rate. The warmer it gets, the more bacteria you get. That's pretty disgusting. But all that being said, that's what this represents. You can determine how much bacteria is in food removed from a refrigerator from fridge after T hours. So that's what it's saying. Terrible handwriting, I know. But what it's saying is, it's not saying that the temperature of the food is independent, but what it's saying is that I assume when you take the refrigerated food out, it was at 2 degrees Celsius at the time, and after this time, it increases. So it's not independent of the temperature, but the temperature has been considered already. When we expanded this out, that's what we found. So we are skipping that part entirely, and we're just saying after this time, we know how much bacteria. We don't even need to know the temperature. We already know the bacteria. Okay, the second one, the number of bacteria in the food when T equals 2 hours. Now you can see why it's important to have this function here, because we can use this straight up. Notice I don't have to go to big T of little t and figure out how many hours it was out of the fridge, which would be what the temperature is. It would be 10 degrees Celsius, by the way. But I can go straight into N of T of 2, which is this function right here, 320 times 2 squared plus 420, which becomes, 1280, plus this is disgusting to think about. I really don't know how bacteria appears or if you can see it. This is just on the spot kind of stuff. 1,700 bacteria in a food item that has been left out of the fridge for 2 hours. Ugh. All right. The time when the bacterial count reaches 2,000. So this time we are going to substitute 2,000 for N of T of T. N of big T of little t. So 2,000 equals 320 T squared plus 420. Remember, we're just trying to find the time. Subtract 420, we get 1580 equals 320 T squared. Divide by 320. This does not seem to come out cleanly. I almost have to use a calculator for this one here. Dividing that, you get an exact value of 4.9375. Take the square root, and T will be, now it's not plus or minus. You can't have plus or minus hours here, especially given the domain. Not saying you can't have negative hours, because negative hours represents before the fridge stuff, but this is only what we can consider. So the square root of that value becomes 2.222, and you might think it's all twos. No, it kind of stops after that, but it's a 048604. So 2.222 hours is the number of hours it would take to reach your bacterial count reaches 2,000. I want to find out what the bacterial count is when your food is no longer, when you shouldn't be eating it. It must be after 3 hours for that, so we could figure that one out at a different time. So, okay, so there's that last one there. So covered in this section, we did adding, subtracting, multiplying, and dividing functions. We found out which ones were commutative and not commutative. We also did them with graphs, okay? A little bit. We mostly did adding for them, but how you can do them. We determined how to find compositions of one function with another function. We also did those kinds of things, specifically compositions of functions in real life problems. Fiend!